Basically English, but if you have some problems, like our colleague Darwinian have some problems, he prepared this short version for persons who know only English, and it will help them. But presentation will be in English, in Russian. In Russian, if you have some problems, like our colleague, but slides are yes in English. Anyway, I pass the chairing to our colleagues from Georgia, English, and them. But the presentation will be in English, in Russian.
С вашего разрешения я продолжу на русском языке. Наша делегация из Тбилиси, грузинская делегация, приехала вчера, и прекрасная погода встретила нас в Ереване, и мы привезли из Тбилиси огромную любовь и уважение нашим армянским друзьям. Мы чувствуем здесь хорошо очень. Это ваша заслуга. Я желаю вам, желаю всей армии процветания, мира, спокойствия, и чтобы у вас все было хорошо. И уважение нашим армянским друзьям. Мы чувствуем здесь спокойствие и мир. Это ваша заслуга. Я желаю вам. Начинаем. Наше сегодняшнее заседание Hasmik Sarkian on non-convexity of the set of hypergraphic sequences. Please.
Thank you. So my presentation is on the problem of hypergraphic sequences, and in particular, I will focus on convexity-related issues of the set of all the hypergraphic sequences. A brief outline of my presentation is the following. So I will start with problem definition, then I will give interpretation in terms of discrete tomography, binary cube as well. I will speak about complexity of the problem. I will introduce some results, structures, properties, results, and at the end, I will prove that the set of hypergraphic sequences is non-convex set. So I will start with the definition of hypergraph. Hypergraph is a pair where V is the set of vertices and E is a set of hyperedges, and this is a collection of non-empty subsets of V. Hypergraph is simple if it has no repeated hyperedges, and hypergraph are uniform if all the edges has the same size. The size is R. Degree of a vertex is the number of hyperedges containing V, and the sequence consisting of all degrees of vertices is called the degree sequence of a hypergraph. So what is the problem? The problem is the following. The question of existence of simple hypergraph, simple uniform hypergraph with a given degree sequence. This is known as hypergraph degree sequence problem, and this was a long time open problem, more than 30 years, and recently MP completeness of this problem is proved. But however, researchers is continuing and new results obtained in this direction. For example, there are new sufficient conditions of existence of 3 uniform hypergraphs, or some partial class of degree sequences are investigated, etc. So problem is solved by meaning of complexity, but still this is interesting problem and investigations are ongoing. in one of our previous research, we showed that when we consider the problem without knowledge of the sizes of hyperedges, so the question of existence of simple hyperedges with given sequences, not knowing about sizes of hyperedges, then this problem is not easier than the case of uniform hypergraphs. I would also to show the link, the relation with discrete tomography problem. This is in terms of discrete tomography. This is discrete tomography problem when given projections, in this case horizontal and vertical projections, and we ask about existence of the discrete object with these given projections. And also in terms of unit cube, binary cube, this is numerical characterization of subset partitions. In terms of now, if we consider the set of all simple hypergraphs denoted in this way, which has m hyperedges and n vertices, and denote by dmn the set of all degree sequences of these hypergraphs, then it's easy to see that every integer sequence whose coordinates are ranging between 0 and n potentially can serve as degree sequence of something hypergraph with m hyperedges and n vertices. In this meaning, we can say that dmn, the set of all degree sequences, is a subset in the set sigma. So if we define component-wise partial order here, we can construct the diagram of this partial order set. So this is the set whose vertices are ranging between 0 and n, and our set of all degree sequences are somewhere here. Our goal is to show, the partial goal is show that this set is not convex here. For this, we need some previous results, some previous structures and properties, and now I will define, in short, necessary elements here. So we define opposite elements here. We said that two elements are opposite if their coordinates are related in this way. If we see here, then we can say that, for example, if we take 0 to 4, then opposite elements will be 4 to 0. These are opposite elements in this partial order set. We define also interval here. This is if we take arbitrary two vertices with this relation, one is less than the other, then we define the minimal interval spanned by these vertices in the following way. So we said that this is interval spanned by these two vertices in our partial order set. We also need to define boundary elements in terms of set of degree sequences. We define upper boundary and lower boundary elements. Upper boundary is an element such that any other element greater than this one is not hypergraphic sequence. And similarly, we define lower boundary elements. And the main result, one of the previous main results in this direction is that the set of all hypergraphic sequences is a union of intervals spanned by upper and lower boundary elements. So this is union of intervals spanned by upper boundary elements which are opposite. Now, the goal of this presentation is to show that this set is not convex. So on that example, I will show, so this is the example when n is 3, m is 4, and in the red color, I showed the set of hypergraphic sequences, and in the dark red are upper boundary and lower boundary sequences. So we see here that the whole set is a union consisting of pairs of upper and lower boundary elements. On that example, I will show the example. Now, if we speak about this sigma set, this is a lattice polytope. This is a lattice polytope, a convex hull of a set of points in dimension n, whose coordinates are integers ranging between 0 and n. So each interval spanned by vertices, by opposite vertices, is convex. Is obvious that this is convex set in this sigma, and our goal is to prove that while every set is convex, the union is not convex in this sigma. So, accepting the boundary cases when m is 1 or 2 to n minus 1 or 2 to n, excluding these boundary cases, so the whole set is not convex. I will show you instead of proving, I will show you in an example. So, in red vertices are our set of all degree sequences. If I take these two on 0 to 2, 3, 3, 3. So this two on 0 to 2, 3, 3, 3. We see that these two vertices are comparable. So if we consider the interval spanning by these two vertices, we see that these vertices in blue color also must be included in this set. But these are out of the space of DMN, the set of all degree sequences. So we prove that if we take these two, for example, these two vertices or comparable vertices, then the interval spanned by these vertices contains points which are out of the DMN. And the next result, we found the smallest convex set containing DMN. The smallest convex set containing DMN, this is the following. If we consider union of all intervals spanned by opposite elements, so not just opposite elements pair by pair, but if spanned all lower boundary and upper boundary elements, so this is the smallest convex set that contains DMN. So these are the two main results concerning convexity questions that I would like to present. Thank you for your attention. I left time for questions. So these are the two main results concerning convexity questions that I would like to present. I left time for questions.
A new sufficient condition for a two-stroke graph to be
When we say new condition, when we say new condition, this is not all
Ne gerekmiş?
Դեկատիվում պրեզենտացիայի մոդից դուրս գան, պրոստը լենասն։ Դες PDF եմ սարքել, որ պրեզենտացիա ալին գոնե ինչ-որ ձևան։ Հասկրոլով կլնի ան։ Սանենք։ Այսին կարող է չթայլ։
Все рационально, չէ՞։
Ահա, սրանը ոչ։
Ահա։
Հմհմ։
Բարև ձեզ։ Мы будем рассматривать конечные орграфии без петель и кратных дуг. Между двумя вершинами разрешается не более двух дуг. В каждом направлении не более чем один дуг. Степень, входящий, это количество дуг, которые исходят из вершины X. А заходящая степень – это количество дуг, уходящие в вершину X. Степень вершины X определяется как сумма d плюс x d и d минус x. Путь в орграфе – это орграф с множеством вершин x1, x2, xn и множество дуг x1, x2 и так далее. Цикл получается из пути после добавления дуга xn, x1. Орграф называется сильно связанным, если для каждой двух вершин существует путь из x в y и из y в x. И орграф называется косвязным, если количество вершин орграфа больше или равно k плюс 1, и для любой подмножества вершин орграфа D с количеством не больше, чем k минус 1, после выбрасывания вершин подмножества остается сильно связанный орграф. Орграф называется Гамильтоновым, если он содержит цикл, который проходит через любой вершин. Известно, что определить орграф или граф является Гамильтоновым или нет, в общем случае является МП сложным задачей. Но есть множество достаточных условий, при которых, которые обеспечивают гамильтоновый цикл, обеспечивает, что граф имеет гамильтоновый цикл. Здесь мы перечислим следующие общеизвестные и классические теоремы. Ну, Нэш Вильямса, Гуягури, Вудала и Мейнела. Отметим, что теорема Мейнела из обобщения всех трех предыдущих теорем. Кроме того, известно, что сразу видно, что теорема Нэш-Вильямса из следствия из теоремы Гуяури, но там не требуется, что граф быть сильно связанным, так как сильно связанность следует из условий теоремы, что полустепени исхода и захода больше или равно половине вершин. Нэш Вильямс предложит следующую проблему. Характеризовать все экстремальные орграфии для теоремы Гуягури, то есть характеризовать все негамильтоновые орграфии с минимальной степенью n-1. Для этой проблемы Томасен доказал теорему, которая характеризует структура орграфов, которые не являются гамильтоновыми. Подобные задачи я рассматривал и получил тоже похожий результат, который обобщает теорему Томасена. Кроме того, доказать, что если орграф, негамильтоновый орграф с полустепени захода и исхода не более n-1, если содержит цикл длины m, то этот граф тоже содержит все циклы от 2 до длина максимального цикла. Для Нэш-Вильямса, Томасен и я, соответственно, когда n четный и нечетный, получили следующие теоремы. Ну, эти две теоремы были различные формировки, но я здесь соединил их в одной теореме. Ну, кроме этих исключений, все исключения полностью определены. Теорема для теоремы Вудала, Чанг и некоторые доказали, что если условия теоремы Вудала мы снижим нижнюю оценку на 1, то почти всегда тоже теорема верна, кроме некоторых исключений. Для теоремы Мейнера доказано, что тоже верно, если мы снижим только нижние нижняя граница на один только для одной пары вершин, не смежных вершин, то тоже эта теорема будет верна. Этот результат доказывает гипотезу Манусакиса, предложенную в 1992 году. Марк Голдберг и доказали, что если у теоремы Гуя-Ури все вершины имеют степень больше или равно n, а одна вершина имеет степень n минус 1, то орграф тоже Гамильтоновый. Этот последний результат неулучшаемый в некоторых смыслах. Я доказал, что если в двухсвязном орграфе с n вершинами n-1 вершин имеет степень не менее чем n, а n-вершина имеет степень не меньше чем n-4, то D является Гамильтоновым. Доказательство до последнего результата нигде не опубликовано, было опубликовано, но по просьбе моего друга и коллега Григория Гутина я попробовал доказать, представить доказательства этой теоремы. В результате я нашел, доказал следующая теорема 7, который утверждает, что если орграф, двухсвязный орграф имеет n-1 вершин имеет степень не меньше, чем n плюс k, где k неотрицательное целое число, а одна вершина имеет степень не меньше, чем n минус k минус 4, то орграф является Гамильтоновым. Ну, при k равно нулю это обобщает мой первоначальный результат. Доказательство теоремы 7 состоится из двух этапов. Сначала я доказал лемма 1, который имеет самостоятельный интерес. И теорема 9, который утверждает, что если орграф, двухсвязный орграф имеет цикл длины n минус k минус 2, то этот орграф является Гамильтоновым. Кроме того, из этой теоремы наверх, тоже получается достаточные условия для гамильтоновых связным орграфа. Который есть аналог у дальше. Но здесь нужно отметить, что есть многие достаточные условия гамильтоновости для обыкновенных графов, где пользуется любая связанность. Но для орграфа в общем случае, ну, мне неизвестно, что орграф К-связанный и имеет гамильтоновый цикл. Ну, очень интересно будет, если найти такие условия. Кроме того, предложены некоторые проблемы.
И вопрос, там вы говорите за исключение некоторых случаев.
Все эти случаи описаны.
Это понятно, но это бесконечность?
Нет,
Или какие-то конечные количества?
Ну, можно сказать, для каждого n есть орграф.
Регулярный.
Это понятно, но я опять спрашиваю, это бесконечная семейство графов? Անվերջ տանի, թե մինար վերջավոր տանակի գրաֆն։
Перчало. Ну, конечное число. Ну, для каждого n есть такие орграфы.
Но вот тогда получается бесконечная семейство. Если для каждого n есть граф, то это бесконечно. Нет.
Еще есть вопросы?
Он ваш-
Теперь еще раз попробуем.
Прошу, посмотрите, пожалуйста.
Да. Нет, это не перечислить. Йога не только снять, large size, graphs, graph conjugation of property and young или young. Young или young.
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 Young. Das ist doch, wer wird schon gehen? PowerPoint açarsan, bunun da Hochler, was war gut, ja? Точно. Лахоки. Здесь. Տեքստը վերև ներքև։ Ակամ երկրորդ էջերն է։ Այս աչքը։ We use standard definitions, the graph and the order or the number of vertices, delta, the mean degree. Sigma lambda, the word minimum emitters here. At the minimum degree sum of lambda independent vertices. Called the connectivity C, longest cycle in J. C, the length of the longest cycle of the circumference. This notation, the length of the longest cycle in minus 3. And this is the length of the longest cycle. The next. Boundless conjecture. That is, the graph is lambda connected. This condition, degree sum condition. Under this condition, the graph then minus 3 has a path of length of which at most lambda means lambda minus 1. This conjecture is a common generalization of a number of well-known results, including control and domination cycles and special cases. The mean degree version of this conjecture would here we consider the minimum degree condition of this results theorem A, B, C, D has obtained these are improvement of minimum degree conditions. That is the conclusion. This conclusion is strengthened to this condition. Here, the minimum degree condition, this minimum degree condition was weakened to this. This is the next improvement, and the minimum degree condition is weakened, and the conclusion is strengthened. These are improvements. We obtained the following results that we call modifications. That is the conclusion lambda minus 1 is replaced by this condition. we call this modification because this is not a special case of Jung's conjecture. And the following next modifications, the connectivity conditions were replaced by this modification. This condition was replaced by improvement under the following modification and the next modification. Jung's conjecture is a reverse version of Jung's conjecture, and the following results are very symmetrical to results with respect to Jung boundary conjecture. These are the similar improvements and which are known. And in this, and we prove the following results, modifications about Jung's conjecture. Modifications. This is one modification. The next modification. Two modifications, improvements and modification, and modification for connectivity condition and improvement. Here is improvement and modification. Conclusion are the same. Differences. The results are obtained, the known results are obtained in these two papers. Thank you.
Thank you. No? Thank you. Next presentation on the and on the engagement chromatic sum of the Fibonacci groups.
Hello, my name is Hamlet Mikhailyan. I'm a PhD student in Yerevan State University, and I'm happy to present our work, which we have done together with my scientific supervisor, Mr. Petrosyan. In the graph theory field, the topic is edge colorings and specifically edge chromatic sums of specific types of graphs. Let's start with some definitions and some known results on this field. Everything starts from vertex colorings. Let's define what is a proper vertex coloring. A proper vertex coloring is a assignment of vertices to natural numbers in a way that every adjacent vertices have different numbers. In this case, we call this number a color of vertex. We denote by sigma G alpha the sum of the total sum of colors of all the vertices in the graph. And finally, we define the vertex chromatic sum as the minimum such sigma G alpha among all possible proper vertex colorings of G. In other words, we want to color the vertices of the graphs in a way that the adjacent vertices have different colors, and the total sum of these colors is minimal. It's understandable that there can be more than one such colorings for which the minimum sum is achievable. So all those colorings are called sum vertex colorings, and the strength of the graph is defined as the minimum number of colors needed for a sum vertex coloring of G. This concept of sum vertex colorings and vertex chromatic sums was introduced by Supovit and Kubica in 1987 and 1989, respectively. Let's see what results do we have in this field. It is known that the problem of finding the vertex chromatic sum is NP complete in general, and it's polynomial time solvable for trees. There are also some results. For example, we have some approximation algorithms for vertex colorings of specific types of graphs. We also have some limits, some bounds, lower and upper bounds for specific types of graphs. And what we have about the strength of the graphs, we have a theorem similar to Brooks' theorem, which states that the strength of the graph is less than or equal to delta G plus 1, where delta G is the maximum degree of the graph, and the equality holds only for complete graphs and odd cycles. It's obvious that the strength of the graph is greater than or equal to the chromatic number of the graph, but it's not always the case that they are equal. In the example illustrated here, you can see that, for example, this graph can be colored with two colors. So its chromatic number is 2, but in order to obtain a lower total sum, we need to add the third color. You can see that in the left side, the total sum is 12, while in the right side it is 11. So in this case, the chromatic number and the strength don't match. All right, this was about vertex colorings. And after this introduction of vertex colorings, later Barnoy, Bellare, and Co. And separately Jaro and Kubale, and separately Haji Abul Hassan, Mehrabadi, and Tusarkani introduced the sum edge coloring and edge chromatic sum concepts. Let's also define them. So proper edge coloring is a mapping, is an assignment of edges to natural numbers so that adjacent edges have different colors. And by sigma prime G alpha, we denote the total sum of the colors of the edges in G with respect to some coloring, the coloring alpha. Similarly, we say that the edge chromatic sum is the minimum such sigma prime J alpha among all possible proper edge colorings. And it's obvious that there is a connection between the edge chromatic sum and the vertex chromatic sum by this relation where Lj is the line graph of J. Again, we call some edge colorings those colorings for which the minimum sum is achievable, the edge chromatic sum is achievable, and the edge strength of a graph, which is denoted by S prime J, is the minimum number of colors needed for a sum edge coloring of J. We also have that it is also known that the problem of finding the edge chromatic sum is also NP-hard for multigraphs. And there are also some approximation algorithms for specific types of graph. For example, there are 2 approximation algorithms and 1.8 approximation algorithms for general graphs. There are 1.4 approximation algorithms for bipartite graphs, and so on. What we have about the edge strength, it is also known that there is a similar relation like in the Wissing's theorem, that edge chromatic sum, that edge strength of the graph is lower than or equal to delta J plus 1. This means that this number can be either delta J or delta J plus 1, since it's obviously is greater than or equal to the chromatic index of the graph. And here is also the case that they are not always equal, the chromatic index and the edge strength, they are not always equal. You can see in this image that they differ. Now let's talk about some applications of these colorings. Let's see this on an example of on a just easy comprehensible example. So imagine there is a party where some people are invited and some of them already know each other, and before the event starts they want to have a conversation. Let's say that we know which people knows whom, and we assume that each conversation takes 1 unit of time. Suppose that each time every person can speak with only one other person. So it's not the case that at the same time the same person talks with some people, multiple people simultaneously. So let's consider the time of endings of all conversations. Our task is to understand how we can manage their speaking timelines so that their average ending time is minimal. So this problem can be brought to the edge chromatic sum problem. Let's see this on an example of more real life scenario, more practical scenario. Suppose we have some processors and some tasks which require 2 given processors. For example, we can say that the task is about sending a message from one computer to another. And here we have again these conditions that each time processor can do at most 1 task, and we need to schedule the processes so that in average the tasks are finished as fast as possible. So these problems are can be brought to edge chromatic sum problem. The vertex chromatic sum has also its applications in parallel computing. There is a version of Dining Philosopher's problem that can be modeled via vertex chromatic sum problem, and so on. Before we can say about our result, let's define what is a Fibonacci cube. Today we talked about n cubes. I will I will describe it once more. So n cube is a graph divided on some vertex set Pn, which consists of all the strings of length n that contain only digits 0 and 1. And when while the vertex set is this set, we said that two vertices are connected to each other when they differ only in one position, in exactly one when their digits differ exactly in one position. This is the n cube graph. For this graph, a lot of things are known. For example, that this graph can be colored with n colors, can be edge colored properly with n colors. We also know that it's obvious that all degrees of the graph are equal to n. So it's easy to understand, to calculate the chromatic sum, the edge chromatic sum of this graph, but it's much more harder to find something about a subgraph of this graph, which is called Fibonacci cubes. They are introduced as follows. Let pick only those vertices from the vertex set of Qn, the string representations of which doesn't contain two neighboring ones, and the subgraph of Qn induced by those vertices we denote by gamma n and call the Fibonacci cube. So our result is the following theorem, which tested for every number, a natural number n, we have an upper bound for the edge chromatic sum of gamma n. And that's it. I can say that for this, for proving this theorem, we constructed respective colorings for each n, and since the edge chromatic sum is lower than or equal to sigma prime G alpha for each proper edge coloring, we obtain this result. And the construction, some images describing the construction are illustrated here. So in the right sides, we can see how we color, for example, gamma 3 and gamma 4. And that's it. Thank you very much.
Hello, my name is Aram Derampyan. I'm a PhD student at Russian Armenian University. Today I'm going to talk about strong edge coloring of Hamming graphs. The results that I'm going to talk about today are obtained in collaboration with my scientific supervisor, Petros Petrosyan. Okay. Let's begin with some definitions. Graphs are finite undirected and have no loops or multiple edges. Denote set of vertices and set of edges of graph G as VG and EG, respectively. Denote the maximum degree as delta G. An edge coloring of a graph G is a mapping of vertices of edges to natural numbers. The edge coloring phi is called strong if the colors for two edges are like colors assigned to different edges. The strong edge coloring phi is called strong if edges receive different colors in case if they are at distance 1 or 2. So in case of proper edge coloring, the edges that share the same vertex should have different color. In case of strong edge coloring, we increase the distance by 1 more. So the Cartesian product of graphs H and G is a graph such that the vertex set of HG is a Cartesian product of their vertices. And two vertices U and U strich and U prime and VV prime are adjacent in the constructed graph if and only if they're either the first or second position in the new vertices are the same. The minimum number of colors needed for strong edge coloring of graph G is called strong chromatic index of G and is denoted by He prime SG. So in this example, we can see the difference between a regular edge coloring and a strong edge coloring. So here we have a proper edge coloring, right? But because these edges are in a distance exactly 1 from each other, it won't be a proper strong edge coloring. So we need at least, we need at least extra edges in between to have a proper coloring. The Hamming graph H and M is a Cartesian product of n copies of the complete graph Km, where both n and m are from natural numbers. Here in the example, you can see an illustration of H to 3. So today, a lot of people talked about n-dimensional cubes. I also want to mention that Hamming graphs are one of the ways to generalize n-dimensional cubes. To be more precise, if we fix the m as 2, so we fix the complete graph of length 2, we receive n-dimensional cube. So H and 2 is the same as n-dimensional cube. So in case of strong edge coloring, the main thing that scientists are looking for is to find out the strong chromatic index and minimize it for different graph classes. So in 1985, during a seminar in Prague, Erdos and Nesetril put forward the following conjecture. For any graph G with maximum degree delta G, this statement should be true. Like it has cases for delta G even and odd. So nowadays, this conjecture is proven only for delta G equals to 3. For delta G equals to 4, we have a result of that strong chromatic index is lower or equal than 21, but the conjecture says 20. So there is a 1 color gap, and that's still an open problem. And now let's talk about main results. Let H and M be a Hamming graph with M bigger or equal to. In that case, the strong chromatic index for H and M is bigger and equal than n times m minus 1 minus m times m minus 1 divided by 2. And the second theorem, let hash and m be a Hamming graph with m again bigger and equal than 2. Then we have this upper bound for our strong chromatic index for Hamming graph. So I want to mention a few things about these theorems. First of all, when we consider the n-dimensional cubes, which means that we fix m equals to 2, the upper bound and lower bound becomes equal to each other and confirms the well-known result for strong edge coloring of n-dimensional cubes, which was proven in 90s. And the other thing that I want to mention here is when we fix m for any graph, so we fix the base complete graph, at that point, the difference between upper and lower bounds for even cases become a constant number. So for any fixed complete graph, when we fix the complete graph in Hamming graphs, the upper bound and lower bound are, the difference is only a constant number for m when m is even. I think, yeah, like these are my main slides. And because I have a few more minutes, I guess, I would like to talk about a little bit about the proof and what is the idea behind the proof for the upper bound mainly. So the one way to think about Hamming graphs is that we can take a complete graph Km, and instead of each vertex, we can put a component of hash and m minus 1. And hash n minus 1m. So we can replace each vertex with a previous Hamming graph, like with 1 and less, and connect the corresponding edges to each other. That way of construction of Hamming graph allowed us to use a very similar algorithm to a regular edge coloring of complete graphs, for a strong edge coloring of Hamming graphs in general. Yeah. And here is an example coloring of for the same graph as for the same hash 2-3 that I showed previously. Here we use exactly 9 colors for full coloring, and there is no way to reduce that number for this specific case. That's it. Thank you.
ОСАГО нет ничего особенного. Это просто страховка. Цените свое время. Покупайте полис на Сравни сами. На Сравни ОСАГО по лучшей цене и без переплат. Капитальный ремонт в системе нужен. В всей стране капитальный ремонт. Приятно, честно, Александра Великинского. Я за справедливость 93-й.
Вы смотрите «Вести», мы продолжаем выпуск. Потери украинских боевиков за минувшие сутки составили около 850 человек. Это новые данные Минобороны о ситуации в зоне спецоперации, которые мы получили буквально только что. Больше всего военнослужащих ВСУ, почти 450, уничтожено на Донецком направлении. Также в ведомстве подтвердили, что сегодня ночью вооруженными силами России нанесен групповой удар высокоточным оружием большой дальности и беспилотниками по пунктам временной дислокации иностранных наемников и подготовки диверсионных групп ВСУ. Все объекты поражены, цель удара достигнута. По данным украинских СМИ, в результате атаки в районе Одессы повреждена портовая инфраструктура, а также отель, где размещались подразделения ВСУ. В Кривом Роге местный аэродром оперативно
Что не работает, да?
в бомбоубежище. Краснодон, к слову сказать, находится в привезли
Я тебя сейчас отключу.
компании, как
Может быть, кто-то споет за это время? Mhm. Oh. May I start? In very short, I will present you our first initial results that we achieved during the state committee grant, in which we invited foreign researcher. We invited Professor Yura Katona to be consultant in that grant. What we are trying to do in that project? In general, in that project, we try to solve combinatorial optimization problems, not in traditional approaches, not in traditional ways, but we want to use for this machine learning technique. In some problems, for some problems, it is very, very difficult to make all computations, all algorithmic solutions in combinatorial level. And instead of this, we imagine that in a case that we have a lot of combinatorial, a lot of particular instances, individual instances of some combinatorial optimization problem. And we have this large list of examples of this combinatorial problem, and we have solutions. In these cases, we try to find a way to learn to solve this problem. Machine learning in this case is in two stages. In first stage, the program, the system, the algorithm is learning, having the database. After that comes the second stage, and second stage is very simple. It does not require big database, big data analysis, etc., etc. It is just receiving the issue, analyzing small amounts of data, and tries to obtain the result. So this way is, I think that this way will be quite long. And at the moment, we are in the middle of the research. We are doing some studies. Why we invited in that project Professor Kazan? Because all we know, the Hungarian School for Combinatorial Analysis, this is Alfred Rényi, Erzsors, and many scientists, great scientists there. And among them is, of course, Professor Katona. And having direct contacts and some work experience with him, we invited him to work with us in this area of combinatorial optimization, of extremal combinatorial analysis. And at the moment, we submitted some papers. One was focused on machine learning. This is a different story, but in this particular case for our conference, we submitted this paper, notes on reconstruction of shadow minimization Boolean functions. During the plenary session, we were presented with the topic of reconstruction of general monotone Boolean functions. Everything, maybe not everything, but many things are known for reconstruction of general Boolean functions, monotone Boolean functions. Everything is quite hard there. not only NP complete, but a lot of problems are quite hard there. And in a way, when we thought what to do, we came to the idea that instead of considering general monotone Boolean functions, we can consider particular subcases. In this paper, somewhere we listed some examples of this. Here we listed some subclasses of monotone Boolean functions. Here we have threshold monotone Boolean functions, symmetric Boolean functions, and one more class which we call Kraskell-Katona monotone Boolean functions. Some words about this class of monotone Boolean functions. Imagine that we have a finite set of some finite set of n elements, and we have a collection of subsets of this finite set. Let we are interested in subsets of this general set of size I, of some size, some fixed size. Of course, number of subsets of size I of this n element set equals n choose I. But in our case, when we have a collection of subsets, then which parts of I subsets are included in at least one of these subsets of this collection? So I wanted to go without definitions, but again, let I go to the picture. This is n cube. In this n cube, we have the general set consists of 5 elements. If I take one subset of elements, let's say this one consists of 3 elements of these 5. And if your I is here, then these subsets belong to this one subset. Now, if I have not only one, but I have a collection of subsets, one is this one, one is this one, one is this one, and each one will cover some elements of this layer, and all they together will cover some part of this. We call this shadow. Shadow of this collection of subsets of a finished set. So many years ago, but no more than 15 maybe, Kraskell and Katona independently, they obtained a result that to minimize this shadow, you need to have this, you have to how to say, you have to place these subsets in a collection by a lexicographic order. The initial proof was just for the case when your collection is taken from some layer K, and your target is in K-1 layer. You want to minimize all collections of size k minus 1, having some collection in upper layer. After that, this famous result obtained by our colleague was extended a bit, generalized, in a way that they considered not only 2 layers, but many layers, and we want to minimize the shadow in a fixed layer. In this case, we obtain some monotone Boolean function. Because the theorem says that if you want to minimize the shadow in one layer, then you have having the sizes of your subsets, but not them exactly. Having the sizes, you have to choose the given number in this layer in a lexicographic order. And then another examples will continue the lexicographic order in other layer, etc., etc. So anyway, I will stop here by this. And in this way, we get some new interesting class of Boolean functions because of the general problem is quite hard, quite difficult. Our target is to consider particular cases, particular classes of monotone Boolean functions, and we were attracted by this case because the topic is very close to our interests, and the problems are open, not yet even studied. And here we can report some initial results. One result is about the generalized sets. For monotone functions, there are specific sets. If we imagine, if we represent the monotone Boolean function by the set of its upper zeros and lower ones, each of these collections, upper zeros and lower ones, these are Sperner families, and these 2 Sperner families together, they compose a generalizing set, which have the property that if for some subclass of monotone Boolean functions, if there exists this kind of generalized set of vertices, then any 2 functions that are equal on this set, generalized set, then these functions might be identical. They might be equal to each other. So not all classes of monotone Boolean functions may have these generalized sets, but we prove that this class, Kraskov-Katonah class of monotone Boolean functions, they have this property. And after that, we obtained some estimates about the size of this set. Next fragment of this research is devoted to reconstruction algorithm of these kinds of functions. In this case, during the plenary session, Professor Katonah was telling us about Hansel chains. Hansel chains are special chains in n-dimensional unit cube. They give a quite good instrument for a reconstruction of monotone Boolean functions. Of course, we use this structure, but besides this structure, we also use that we have lexicographic order, and in each layer, we have to continue lexicographically the shadow of the upper layers. Having these two instruments, we could think about minimization of algorithmic parameters during the reconstruction, and also this part is presented in this paper. Last point that we are speaking about in this paper concerning classical Catalan Boolean functions is about size of these sets for how many n-dimensional monotone Boolean functions belong to this class of classical Catalan. Also here we have some results, which is 2 in power n. If you remember that all Boolean functions are 2 to n, of course, this is very narrow case, narrow family of Boolean functions. And anyway, we are at this point. We have some combinatorial investigations and some combinatorial results. And of course, our final target is how to move all this opera to machine learning area. We have two parts. In one paper, we have the machine learning part. In this paper, we have combinatorial part. And still how to combine all these things into one idea, into one joint work. This is our problem for near future. I can say only this much. Professor Patton, do you have questions?
No questions. Thank you.
Thank you.
It's not very much. I was thinking more. We continue here.
Нету никого. Ну, сейчас вот все это отключим.